All right, do group 1 cations form complexes and the ligand's going to tag? Well, one of the things is group 1 doesn't have a very high charge to size ratio, except for maybe lithium ions. And so they aren't as reactive. Group 1s just in general are not very reactive. They're kind of big with a low charge. Do you remember what happens to size as we go from left to right in the periodic table? Does it get smaller or does it get bigger? It gets smaller. So the group 1s are kind of big, and then it goes smaller as you go across the periodic table. It gets smaller because of what? Z effect. And so, group 1s. What about group 2s? Group 2s are smaller in size, have higher charge. Shouldn't they participate? Shouldn't we be able to do that? And the answer is group 2s can participate in complexes. Let's take a look at a complex like chlorophyll. Bring that up. Chlorophyll. Let's take a look at the structure for chlorophyll. If we take a look at the chlorophyll A, chlorophyll B molecules, this is big molecules. A lot of biological molecules are quite big. When we look at this molecule, there's mostly hydrocarbon right here. But take a look. There's carbon, hydrogen, oxygen, nitrogen kind of ring system here. Do you see the ring system? And then in the center of that ring system is what? A magnesium. And so magnesium is an essential element for chlorophyll. And take a look at the bonding to the magnesium. It's kind of interesting. It kind of looks square planar, but I can tell it's probably not perfectly square planar. Why? Actually, we need more because of these dashed. Usually dashed means, dash could mean two things. One, dash is an IMF rather than a bond, or dash could mean it's either going out of the plane up or out of the plane down. We usually use wedges for out of the plane up and dashes for out of the plane down. But this is kind of funny because this, when I see a solid line like this, I think in plane. So how can it be in plane and out of plane at the same time? Because this ring system consists of what hybridization? Can you tell the hybridization in the ring? It's all sp2. This is all trigonal planar. This whole thing is flat, like a pancake. It's kind of an interesting ring. These are aromatic rings where we have this pi. Remember the delocalized pi bonding network? Anybody remember the delocalized pi? Where have you seen the delocalized pi bonding network before? There's an example in Chem 1A, the benzene ring. Classic, right? The benzene ring. There's some similar to that. There's lots of organic compounds like that where you have this sp2 network of all the p orbitals line up, so you can have the delocalized p pi electron. Well, going here, magnesium is actually bonded. It's not just stuck there. It's actually bonded in this particular complex. But magnesium, are there very many complexes? No, the vast majority of complexes are going to occur not with the group 1, not with the group 2. In fact, group 1, can complexes occur with group 1? The answer is yes, except, the type of bond that's there is exceptionally weak. It's more of an IMF rather than a full covalent bond. We'll see that in a minute. Like, for example, sodium ion. Well, sodium ion is going to be attacked by the base or the ligand because it's positive. The base is negative charge density, and so there's going to be attraction there. The attraction, So to answer your question, the question is, does it participate in complexes? Well, it depends on how you define participation. How strong of a bond do you need before you say, okay, that's a covalent bond? Because the bonds are just going to increase in strength, right? And there's going to be, it's not going to be quantized. There's going to be an increase that depends on the charges, the charge separation, that type of stuff. The increase, though, goes like this. So what you have to do is you have to come up with a cutoff. And we saw this exact same problem when we're trying to look at what defines a nonpolar bond, what defines a polar covalent, what defines an ionic bond. You know, is there a quantum level jump? And that is, when you go from a nonpolar bond to a polar covalent bond, is there a quantum jump there? And the answer was no, there's no jump. What happens is you have a transition. This is a figure from Chem 1A that we call a percent ionic character versus delta En. And then we just saw, you know, there's a smooth variation. The greater the difference in electronegativity, the more ionic that bond is. But where exactly do we call it ionic? Should we call it when it hits 50% ionic character? So if it's like 50.5%, all of a sudden we call it an ionic bond? Anything from 50.5% ionic to 100% ionic is called an ionic bond? No, it's somewhat arbitrary, do you see? It's a little bit arbitrary in that sense that, okay, yeah, so the easiest thing to do is not to try to classify it. You know, we can come up with some simple classifications. Greater than 50%, we'll call it ionic. Less than 50%, we'll call it covalent. Is that how we should do it? No, we had some very crude approximations. If the delta En were less than about 0.5, we call it nonpolar covalent. From about 0.5 to about 2, we call it polar covalent. Above 2, we'll call it ionic. But are those hard borders? No, it's just kind of trying to group things into a sensible classification, right? And so when we say sodium ions do not participate, well, sodium ions can be attacked by these, but they aren't going to form these stable complexes, right? But they will form something. You know, it's just not, and therefore we call it like a hydrated ion rather than a complex. Therefore, we'll call it more of an intermolecular force rather than a covalent bond. And so we'll see different levels of interaction. All right, with that said, then, the way we're going to classify it is sodium doesn't. Group 1 doesn't, you know? Because it's like a carbon-hydrogen bond. The carbon-hydrogen bond we call nonpolar, but is it truly nonpolar? Is that truly nonpolar? No, it's not truly nonpolar. There's a slight dipole moment. That dipole moment is so tiny, though, so, you know, that's close enough to nonpolar. We'll call it nonpolar. Right? And so in the same way, when I say group 1 does not participate, it's in the exact same vein as this, saying that, okay, it doesn't participate because the interaction is so weak, we just kind of ignore it, but there is an interaction there. Does that make sense? So, basically, the simple thing to say is these form just for transition metals, but they don't. You know, magnesium too, and chlorophyll does. Form that. So, what we'll do is look at some examples of complexes. But first, I need to answer a question that came up regarding the homework. And what number was that? What chapter? 24 or 42. Oh, just read it out to me. I was going to pull it out. What's the question? Asking for.
Explain the following observations to a series of equations. The readings are forms glutamate. After a day or two, the solution is violent. When the vitamin solution evaporates to dryness, a green solid remains.
Okay, the first thing, what did you call that? Chlorine chloride? No, chlorine chloride is chlorine. Chlorine chloride? Chlorine with a chlorine? Oh, chromium chloride. Do you call it chromium chloride, or should you call it something more specific? You know about transition metals. All transition metals have variable charge except for three important ones. What three transition metals have fixed charge? Silver, zinc, and it forms an L in the periodic table. Somebody tell me, how can I enable pop-ups in Explorer quickly? Oh no.
Have you tried the file on the left, the top? Yeah, that's one of the things that can
Under 5.
There you go.
Okay, thanks. Okay. What is it? Silver, zinc, and well, I heard nickel. Nickel in Chem 4 they say is fixed charge, but nickel has more charges. 90% of the compounds are nickel 2, let's say, but there's also nickel 3. And so there, since we're in Chem 1B, we're going to consider nickel a variable charge rather than a fixed charge, because otherwise we'll miss about 10% of the compounds, something like that. And so what else has fixed charge? Like 99.9% of the compounds are going to have this charge. Cadmium, right? So that's good. Well, how was your review coming along? Any Chem 1A stuff? Giving you trouble? There's different things you could do for that. What number was it? 42? Okay. Well, these hydrated compounds like this. This is actually called chromium because it's variable charge. It's called chromium 3 chloride. Chromium 3 chloride. We wouldn't necessarily call it chromium trichloride because we usually reserve that for molecular compounds, not ionic. And so we call it chromium 3 chloride hexahydrate or .6 hydrate. Right? Now, where are the waters of hydration in this? Where are the waters of hydration? Are they on the chromium? And the answer is actually, normally when we're thinking about this, and let me go back to the beginning of this chapter, talk about Werner. We normally think of the crystal lattice, right? And in the crystal lattice, there are gaps, which we call holes, in which things can fit in. Usually, they're empty. Do you guys remember the tetrahedral, octahedral holes? Briefly, no. And so when we're looking at, actually, let's look at something. We'll go to FCC. Remember what FCC stands for? Face center cubic. So I'm going to go to octahedral holes and an FCC lattice. Let's see if we have some images for that. Yeah. this is tetrahedral holes here. You can have some octahedral. This would be some octahedral holes. All right, the big atoms here form the FCC lattice. And then there are some empty spots. In the empty spots, small atoms or ions can fit. And also small molecules can fit in there as well. And so if we have a lattice like this and something can get absorbed into the structure, then that might be a hydrate. And so let's say we have a crystal lattice like this and some water molecules in the gas phase, it's humid, get stuck and they work their way into these holes, then we'll have a hydrated lattice, right? There's a limited number of waters you can fit per formula unit of lattice. So that's that. Here you can see it detailed. This would be an octahedral hole here. Octahedral. Underneath here we have something called a tetrahedral hole. There's one more which is like a trigonal hole, but that's so small we don't really worry about those, even though they're talked about in Petrucci. And so it was thought that water, well, ammonia, if there's ammonia vapor in the air, you'd smell it, right? And what happens if the ammonia comes into contact with the crystal? Well, the crystal, there's a whole bunch of charges, positive charges, negative charges from the ions, right, the ionic lattice. And those ammonias can get stuck on the surface, and then they can work their way into one of those holes, right, and get stuck in a hole. And so what was thought of is this is a cobalt-3 chloride lattice with ammonia stuck inside the holes, whatever holes they can fit into, octahedral, tetrahedral, whatever else. Same thing with this. Well, it turns out we can fit a maximum of 6, 6 is the maximum occupancy per formula unit. Here. But we can put fewer in. For example, we could put just 5 in and leave one of them empty. It depends on how much ammonia you expose it to. Right? Well, how can we get rid of the ammonia? One way you could get rid of it is just heat it up, right? The vibrations will knock the ammonias out back into the air, right? And so the same thing. Okay, 5 ammonias are in there. This is Alfred Werner. Do you know about him? Alfred Werner won the Nobel Prize for figuring out this class of compounds, the coordination complexes. And up to this point, these strange structures weren't known. So you have something like this. Take a look. That's one way of knocking out the ammonia. Just heat it up, right? What if I dissolve this? Is cobalt-3 chloride soluble in water? I'm going to try to make this quick. Yes, chlorides are all soluble except for silver, lead, and mercury. And so if I dissolve this, by dissolving it's going to break apart the lattice and free up the ammonia. And so if I dissolve this, what will the inventory be? Cobalt-3, 3 chlorides, and 6 ammonias. So the cobalt-3s are moving around in solution, the 3 chlorides are moving around, and now I have 6 ammonias dissolved in water that are moving around. So now I have 3 independent species moving around, right? Cobalt-3, chlorides, and 3 types of species moving around. And ammonia. Does that make sense? All right, now what's one way to test for chloride? Do you know a good quick test for chloride? Add silver nitrate. If you add silver nitrate, you should get a white PPT of silver chloride. This is called qualitative analysis. For example, if we want to test for the presence of chloride, we add a little bit of silver nitrate. If we've got a white PPT, should be silver chloride. There could be interfering species, like bromide, iodide, fluoride. And so there's potential for interfering. But nonetheless, if I dissolve this and add excess silver nitrate, I should precipitate out how many moles of silver chloride for every mole of this? 3 moles. And the same thing here. I just have 5 ammonias rather than 6. And so if I dissolve this, how many moles silver chloride should I precipitate? 3, the same, right? Ammonia, well, ammonia is tricky. You'll learn later that if there's ammonia present with silver ions, ammonia loves to attack silver ions. And we'll see that later. But anyway, that's our prediction here. Well, when they dissolve this stuff, you know how many moles of silver chloride were precipitated? You guys already read this? You should always read it. I mean, here you don't have to read it in depth, all the history, because I didn't really talk about it, but you just skim it, right? And the stuff that I talk about in class, you should read in depth and make sure you understand that thoroughly. But this, well, now I'm talking about this, so you should read it in depth. How many moles of silver chloride formed? 0. No chloride precipitated out, or 3. 3. Actually, 3.
Yeah.
3 moles, just like you'd expect. You know, you dissolve this, 3 moles of chloride precipitate out. And the same thing here. You'd expect 3 moles of chloride to precipitate out with silver. Well, how many precipitated out? Only 2. All right, now, how about this? Do you know how many moles of chloride precipitated out? None. 0. And so I was trying to figure out what was going on, and so Werner came up with an explanation. The structure, the structure where these ammonias just fit into these little gaps in the crystal and are stuck here is wrong. What holds ammonia in a little gap in the crystal? What holds the ammonia in that little gap in the hole in the crystal? Is it a bond? No, it's an intermolecular force, IMF, which we call what? How would you describe this force? It's not called London. London is present in everything with electrons, so there are London forces, but what's the most important? Ion dipole attraction. This is ion dipole attraction holding those in. And so what Werner won the Nobel Prize for is he says, these aren't just molecules of hydration or solvation or whatever. These are actually bonded to the cobalt. And so it turns out that cobalt here with ammonias, the ammonias aren't just stuck in void spaces, interstitial sites, they call them. They're actually bonding to the cobalt, and they're bonding to the cobalt via coordinate covalent bonds in a Lewis acid-base type reaction. So when you expose this crystal, cobalt-3 chloride, to ammonia, the ammonias go in there and attack the cobalt and actually bond to it. How many cobalts can it bond to? How many ammonias can bond to a cobalt? 6 ammonia. What about the chloride? The chlorides are just held together by ionic bonds. And so now the crystal lattice is totally different. Now I've got this cobalt-3 stuck here, and then I have these 6 ammonias actually bonded to it. Here. So I got 6 ammonias attacking them. And so this whole big thing now is my cation. This is going to be net charge 3+. It comes from cobalt being 3+ and the ammonias being 0, neutral. And now I build up my lattice. The lattice is going to consist like this. If I draw the Lewis structure for the lattice, this is a semi-condensed Lewis structure because I didn't expand the structures of ammonia here. I'm going to have 3 chlorides. And so now I'll build up my lattice like this. And chloride will want to surround itself by as many cations as possible. And each anion will want to surround itself by as many. I just repeated that, sorry. Basically, all the anions want to surround itself with as many cations as possible, and each cation wants to surround itself with as many anions as possible, and we build up the 3-dimensional ionic lattice. What holds the chloride and this cation together? An ionic bond. What holds the ammonia to the cobalt? It's a covalent bond. So what we have is we have a complex cation and just a standard anion, just your normal run-of-the-mill chloride anion. And we build up the ionic lattice like this, so that when we dissolve this, the cobalts and the chlorides break apart from each other, but the ammonias break off the cobalt. No, the ammonias are stuck on there. In other words, when you dissolve covalently bound species like when I dissolve ammonia in water, ammonia gas, and I dissolve it in water to form ammonia AQ, do the hydrogens break off the nitrogen when it dissolves? No, it's a covalent bond. And so the same thing here. These ammonias are not going to break off the cobalt. In fact, when I dissolve this in water, what am I going to see? When I dissolve it in water, what I'll see is rather than having cobalt 3, I have cobalt NH3 6 plus 3 plus cations AQ, right? And then I have chlorides plus 3 chlorides AQ. This is the solution. When I dissolve this solid in water, this is what I get. These aqueous cations and these anions here. Does that make sense? So these strange results with the chloride precipitation is due to this. Ammonia is a better, what we call base, Lewis base, than chloride. And so ammonia preferentially attacks cobalt. And we have a name for that. We say ammonia is a better ligand than chloride. So ammonia will attach preferentially to cobalt. Now when we dissolve this in water, what do we form? Well, we've got the cation, hydrated cations, and hydrated anions. This would be the inventory of this solution when we dissolve in water. Now what about this? Well, cobalt has a coordination number. How many things can we fit? Okay, now coordination number is not how many things we can fit. Coordination is. Coordination, it's 6 coordinate, right? Coordination number has a slightly different definition. The definition of coordination number is how many atoms are bonded to it. And so here, how many atoms? We got 6 nitrogen atoms bonded to it. So the coordination number is 6. The coordination also happens to be 6 because we got 6 ammonia ligands. Ammonia as a ligand we don't call ammonia anymore. Do you know what we call ammonia as a ligand? Amine. And so the name for this is hexamine cobalt 3 chloride. And so the cation name, whenever we have an ionic compound, we name the cation first and then the anion. Anion's simple, chloride. Cation's a little bit difficult, but this is hexamine cobalt 3 chloride. We'll write these down later. Well, the coordination number of cobalt 6, if we only have 5 amines attack cobalt, then there's room for one more ligand. That one more ligand in this case will be chloride. And so chloride's going to come in and bond to it covalently. And so these two chlorines are totally different. The chlorine within the complex is covalently bonded to cobalt. These chlorides out here are ionically bonded. And so when we dissolve it, the ionically bound chlorides will be pulled off, the cation, but the covalently bound chlorine will not be. Here. Now, how do we name this? Now they're two different. When we look at the cations, they're two different ligands. And so how we name these is just by alphabetical order according to the name. And so here this is called pentaamine. Yeah. Now rather than calling chloride, we call it chloro when it's in a complex. Most anions we just change the ending to O. And so this would be pentamine chloro cobalt 3 chloride. That's the name for this. Here's the pentamine chloro cobalt 3 cation. Notice it's +2, but I call it cobalt 3. Why? because the plus 2 is the net charge. When I say cobalt 3, I'm talking about the charge on just the cobalt. And I put those in Roman numerals. So this is why if there's 4 amine ligands, then that means how many chloroligands must attach? 2. And that means if I'm looking at tetraamine dichloro cobalt 3 chloride, how many moles of silver chloride am I going to precipitate? Only 1. And so Werner won the Nobel Prize for figuring this out, because most people, when they think about ammonia or water getting sucked into the crystal, they think of the crystals being like a sponge, and the water or the ammonia is just in these pores in the sponge. But in reality, it isn't that way. In reality, it actually covalently bonds to it via a Lewis acid-base reaction to form a complex. And so here we can see some. I mean, on the left here is the hexamine cobalt 3 chloride. On the right here is pentamine. Look at the dramatic difference in color just by having 6 ammonias versus 5 ammonias. If it were just like a sponge, it wouldn't have these dramatic differences in color here. All right, so when we go back to this exercise, maybe this is...
What are the uses of
complexes? Lots of uses for complexes. Complexes are used in industrial chem and biochem. So here, let's just look at some uses for complexes right now. Can you name this complex? Diamine, dichloro, platinum. This whole thing's neutral, so the charge on platinum must be 2. And so this is diamine, dichloro, platinum 2. Well, there are 2 structures that you can have. These are called isomers. Isomers are the same formula, different structure. The 2 structures, this is square planar. And so you could have the chloros adjacent, the amines adjacent, or that you can have them opposite, like this. If they're adjacent to each other, we call that the cis isomer. If they're opposite each other, we call it the trans isomer. And this goes by a common name, platin. So this would be called cisplatin, this would be called transplatin. Cisplatinum is a cancer-fighting drug. Cancer-fighting drug, they call it a chemotherapy agent or a chemical therapy agent for fighting cancer. And cisplatin, because of its shape and the charge density, cisplatinum can bind to a groove in your DNA and prevent what they call replication. Well, you don't want it to bind to a groove in your DNA. You want it to bind to a groove in the DNA of the cancerous cell to prevent that. Transplatinum, because of the charge densities different, will not bind. And so this is active, this is inactive, based on its three-dimensional structure. And so that's one use for this. This is how we synthesize this stuff. Another use is this, cobalt-3. Cobalt-3, one thing you should know is cobalt-3 is an extremely powerful oxidizing agent. In fact, it's too powerful to exist stably in water. And so if you try to make a cobalt-3 solution in water, what happens is the cobalt-3 will automatically attack water and oxidize water. When water gets oxidized, it forms oxygen gas, as it strips the electrons off the O2 minus in water. And so cobalt-3 is too powerful to exist in water. See, it's strong enough to oxidize water to O2. However, this is the reaction here. The redox reaction is, this is a redox reaction because cobalt-3 here goes to cobalt-2. Water, take a look at what happens. Hydrogen, nothing happens. It's +1, +1. Oxygen goes from -2 to 0. So the oxygen in water lost electrons. This redox reaction, we're going from stronger oxidizer, cobalt-3, to weaker oxidizer. The weaker oxidizer is what? No. Remember, the oxidizer forms its conjugate reducer. And so cobalt 2 is actually the reducer. The oxidizer is oxygen and water. Now oxygen not in water, oxygen in acid. And so we compare the three, cobalt 3 versus oxygen and acid, cobalt 3 wins. So we're going from stronger to weaker, stronger reducer, water to weaker reducer, cobalt 2. Cobalt 2 really doesn't want to lose another electron. Well, how can we stabilize this? How we can stabilize it is by adding ammonia. If we add ammonia to the water, then what happens is ammonia will attack cobalt 3. In fact, we could attach 6 ammonias to it and form hexamine cobalt 3 ion. Well, hexamine cobalt 3 ion is not a powerful oxidizer, because the ammonia helps stabilize it. And so this species can exist stably in water, like this, whereas the other species cannot. And so this, did I tell you about aqua regia? Aqua regia works because gold 3, when you try to dissolve gold 3, you oxidize it, strip off some electrons to get it to gold ion, get the gold ion in solution, but gold 3 is too powerful of an oxidizer to exist stably in water. And so one way you could stabilize the gold 3 ion is by adding a ligand to attack the gold 3 as it's formed and stabilize it. You know what ligand they add to it? Chloride. Chloride attacks gold 3 to help stabilize it. And so this is why you need the nitric acid. Nitric acid is an example of an oxidizing acid or mineral acid? Oxidizing acid. Nitric acid comes in, attacks the gold, strips off the electrons, but that's only half the job because it can't exist in water stably. It's too powerful. And then you add the HCl. The HCl is not, its purpose is not an acid. Its purpose is as a base. You're adding the HCl as a base. The chlorides come in and attack the gold 3 and stabilize it. So it's a very, very interesting reaction there for aqua regia.
How do complexes keep, like cobalt hexa, like hexane cobalt, for example, how does it keep the +3 charge if the nitrogen is donating electrons?
Okay, to answer your question, it can't. It can't keep the +3 charge because if you look at the formal charge now, cobalt 3 is supposed to have 0 valence electrons, and now it should have, and so all of a sudden it should be -3 now. You're right. It shouldn't. It gains those 6 electrons. It shouldn't be, or whatever. It should not be +3. But the bonding is too complicated because our formal charge and our oxidation state, those are kind of based on what we know regarding valence bond theory, that kind of stuff. But the bonding in these complexes is, for example, what would you call this bond? This bond here, I know ammonia, amine, this is going to be sp3. What's cobalt's hybridization? sp3d2, octahedral, right? Is that right? It's wrong. Why is that wrong? Because this is not an sp3d2 bond because valence bond theory doesn't work for complexes. MO theory will work for that. And bonding is a bit more tricky. And so to make your life simpler and harder at the same time, you're going to forget all the rules we talked about. When we're dealing with complexes like this, we don't worry about counting the oxidation state. We don't worry about counting the formal charge. We have the numbering system, which is simple, nothing changes. But it's more difficult because you want to apply the rules that you've just learned or you've been learning and being drilled on, right? Formal charge, oxidation state. It just doesn't make sense because each of the nitrogens should be +1 and the cobalt should now be -3 according to our electron counting rules, right? But we aren't going to do that. For complexes, we ignore all that. We ignore valence bond theory and we just focus on just saying that the bonding is more complicated than we care to discuss right now because it's involves MO theory, and the electron counting rules are specific for counting complexes. This is why I started the semester off by reviewing formal charge, oxidation state, and that kind of stuff, because people get all these things mixed up, and and there are certain conventions and rules that we apply to those. And if you don't have the definitions clear in your mind, then applying all these things gets completely mixed up. And so that's a question everybody asks. Why is all the why is cobalt still 3+? What's going on with the formal charge? I know the oxidation state should be 3+. And so they want to do that. The hard thing is, no, you can't do that. You can't do that. And get the right answer, the same answer as the book. All right, let's read this one. Now we have 3 different ligands here. Let's say we have 2 amines, 1 chloro, and 1 aqua. And so we need to name these. The ligands always get named first, followed by the metal. And so naming this would be, what would amine, chloro, aqua? Which should go first? Amine. Amine should go first. Now, I'm deviating a little bit from Petrucci, because Petrucci says do it alphabetical based on the formula. But oftentimes you'll see the formula is written backwards, depending if they're trying to show what bonds to platinum. Does the hydrogen bond to platinum, or does the oxygen? Oxygen. So sometimes they write the ligand as OH2 rather than H2O to show that the oxygen is bonding to the metal. And so if you're doing it alphabetical, do you do it alphabetical based on H or O? Well, most of the time it's H. Sometimes it's O. And so do you use 2 naming systems, or what? Or do you just do it with the way it's conventionally written, H2O? Like here, do you see what I did with the nitrogen? Here. I tried to show that it's not nitrogen bonding, not the hydrogen, so I put the hydrogens offset. You notice that? Well, a lot of people won't even do that. A lot of people will try to emphasize this by writing these ones on the left backwards. H3N. They write H3N to show clearly that the nitrogen is what's bonding to the cobalt, not the hydrogen. See that? And so, to avoid this, I'm going to just keep one rule. The one rule is we're going to name it alphabetically according to its name. And so I'm not going to look at the element here, nitrogen versus N versus H. I'm going to look at the name, amine versus aqua. Now, I said there are 2 ways of spelling amine. Do you know what the 2 ways of spelling amine are? 2 M's and 1 M. 2 M's always refers to ammonia. 1 M refers to the organic class of compounds called the amines, in which there are lots, like trimethylamine, dimethylamine, propylamine. All those will have 1 M. But when you see NH3 or H3N, it always has 2 M's. And so this one is going to be called amine versus aqua. We go with amine first. Diamine, aqua, chloro, platinum 1 or platinum 2? Platinum 2, because the platinum is 2+, amine's neutral, chlorine's -1, water's neutral. So 2 minus 1 gives us +1.
So
Diamine, aqua, chloro, platinum 2.
How do we know, like, when we write the amine first, or water first, or chloro?
You do it alphabetically. So AM versus AQ. You write AM first.
No, the chemical formula, like.
In the chemical formula.
Yeah, because the first example, like you write amine first and chloro later, and then chloro. And then
Yeah. Okay. Let me talk about that right now.
Yeah.
Yeah, this is there's another rule you have to learn, which is cumbersome. You know, this is just one rule after another rule after another rule, and if you're still struggling with the basic rules, it's always difficult. So this is why you want to keep on top of all the other stuff, because that's how things pile up on each other. Now take a look at how they did this. Amine chloro, well that makes sense. You know, amine goes first, chloro next, right? Amine chloro. But what was that other compound we were looking at? Over here. Let's name this one here. Diamine. Now, did we have these two hydroxides, right? And so hydroxide is called hydroxo. In fact, the anions, whenever you see an I, you just drop the IED ending and replace it with O. So hydroxide gets converted into hydroxo, chloride gets converted into chloro, bromide gets converted into bromo, etc. Diamine, dihydroxo, platinum. This has got to be platinum 4. How do I know? Each hydroxide is -1, so that's -2 plus what gives us +2. It's got to be -2 plus 4 gives us +2. So this has got to be platinum 4.
Is that OH2? Is it H2O then?
Oops. Oh, you're right. Do you see the confusion? You know, Petrucci says do it based on the atom. You know, the atom, like oxygen versus hydrogen. But if he starts writing OH2 rather than H2O, then what do you do? OH2, this is not hydroxide, that's actually water. And so this is diamine diaqua, platinum 2. Now, why did he put the aqua in front of the amine? LMNO. No, the reason he put the aqua first is because he's doing it by alphabetical based on hydrogen. And this is alphabetical based on nitrogen. So H comes before N. Do you see that? Even though he has no here. Just by name. Let's just do it by name. You know why I'm not so strict? Because the naming system is not, this naming system has changed. In the, actually, let's look at this. This naming system, about 5 years ago, the amines would have been written before the chloros. And so the formula would have been PTNH32Cl2. 5, 6, maybe more, in Petrucci. And then all of a sudden they decided, okay, now what we want to do is we want to put the anion ligands before the neutral ligands. And so put all the anion ligands first in alphabetical, and then all the neutral ligands after that in alphabetical. But the name, forget all that about the name. In the name, we just do it all alphabetical, regardless of charge. And so here, we had named this diamine, dichloro, platinum 2. So let's take a look at this. What is this? Well, this is a violation of what I just said, because now the chloro is not, you know, the anion ligands are supposed to be first. And so what I'm going to do for the test is just follow this set of rules. And this set of rules is going to be, yes, we'll do some more visual examples. And then we'll look. we're going to do the anion ligand first. And so here, how would you name this? Hexa-aqua. This is perchlorate. So would this be hexa-aqua? Hexa-aqua. We don't do the name based on hexa. We do the name based on aqua. So A. Hexa-aqua perchloro. Diperchloro.
But isn't the perchlorate not part of the complex?
Is it?
Yes, that's it. The perchlorate is not part of the complex. Whatever is in the square brackets is part of the complex.
So that'd be perchlorate after.
Yeah, and so this would be the hexa-aqua cobalt 3. Actually, no, this is not cobalt 2 because we got to use chloride. Hexa-aqua cobalt 2 cation with perchlorate. So we call it hexa-aqua cobalt 2 perchlorate compound. It's an ionic compound.
Okay, how's it 2 again?
Because each perchlorate is -1. This whole thing's neutral. Water's neutral, and therefore cobalt must be +2. Uh-huh.
On number, for the holders on number 3, for E, they had one with like a letter in the middle of the name. It was triamine, nitrito O cobalt 3. And I was wondering, it was missing something, but what's with the O?
Okay. All right, let me talk about that in a little bit. I'm going to come back to that question. All right, what are complexes used? It's used in photography, fixing film. It's used in sequestering metal ions. Sequestering metal ions is isolating metal ions. You know, this is a very famous ligand. This ligand is what we call a hexadentate ligand. A hexadentate can bond to it in six places. And so this is called sodium ethylene diamine tetraacetato. So sodium ethylene diamine tetraacetato. This ligand is ethylene diamine tetraacetato is a little bit long, so to shorten the name of the anion, they just call it EDTA4 minus, or EDTA for short. EDTA is used for different things. For example, EDTA is used as a food preservative. What happens is EDTA sequesters is like binds. EDTA binds to magnesium ions, prevents bacteria growth, and for food. And when it binds so tightly, it's hard to break off. Because, for example, here, one of these oxygens binds, another oxygen binds, and the nitrogen wraps around and binds, and then this nitrogen wraps around and binds, and these two oxygens wrap around and bind. And so it turns out to completely encapsulate the magnesium, like this. If you look, if I throw in a magnesium in the middle, this is just a metal, generic metal, it'll encapsulate any metal pretty much. Some more strongly, some weakly. You know, like sodium ions aren't very strongly bound here. And so sodium ions can be broken off quite a bit easy, but you throw in a magnesium in there or cobalt in there, it's not coming out. It's going to be caged in there. And the thing is this. You know, to break this whole thing off here, we have to break 6 bonds. It's got a coordination number of 6. And so what you do is you break this one off, and then you go to break the second one off, but the first one reattaches. Right? And so you kind of have to break them all at the same time, otherwise it just keeps reattaching. Have you ever had that kind of situation? Take this one off and go to take the next one off, and the other one comes back on and attaches? It's like one of those situations where it's very difficult to remove. And so we call these a chelating. Chelating for claw. You know, it chelates the metal ions and doesn't let go. And so that's this is the same thing. These are 2 isomers, which we'll talk about later. And so it's a good chelating agent. You could use it in You can use it in food preservation, but do you know another use for this EDTA? Another use for EDTA is in terms of heavy metal poisoning. You know, some people are saying, okay, let's say you have too many heavy metals in your blood. Well, if you inject yourself with some EDTA, what's going to happen is the heavy metal will be encapsulated by the EDTA, and thus prevent the heavy metal from attacking proteins in your body, especially sulfur-containing proteins in your body to react with, right? And then these encapsulated EDTAs are stable, extremely stable, unreactive. They just are excreted out of your system, right?
So having a bullying, does it happen when you like, I don't know, deal with chemicals that
Yeah, there are lots of reasons why people go, might get paint. If you have small children and they're eating lead-based paint, their blood lead level is going to be high. And so I know I said this in, did I say this in Chem 1A? You guys remember this? Chelation therapy. You can buy lots of chelation therapy, EDTA, chelation therapy. I know I showed this before, but it doesn't hurt to see it again. And some of you haven't seen this. But one of the things this chelation therapy is used for is for heavy metal poisoning. And there are two chelating agents available as drugs. One is disodium calcium EDTA, or just called calcium EDTA. The other is just sodium EDTA. Calcium EDTA and sodium EDTA, these can be given intravenously. And what happens is the EDTA will attack. Now, the reason there are two drugs is sodium EDTA and calcium EDTA, one of those is more aggressive. One of those is for, acute levels where you need to bring the heavy metal concentration down fast. The other is less reactive. Which one do you think is more reactive and why? Sodium EDTA or calcium EDTA?
Sodium.
And why?
Weaker bond.
Weaker bond, right? Weaker bond, much weaker bond. And so the only agent here, this is it. The only agent here, the only agent recommended for intravenous IV chelation therapy for children is calcium EDTA. That makes sense, right? Calcium EDTA, because calcium is a stronger bond to EDTA, and so it should be less reactive, right? Less aggressive. Well, this is probably the 50th time I've read this, but each time I read this, I just can't believe it. I mean, it's so sad, In February 2005, a girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary blood lead level of 47 micrograms per deciliter, which would be 47 parts per billion. Is that right? Yeah. A venous blood lead level of 48 micrograms per deciliter obtained 12 days later confirmed the elevated blood lead level. Okay, complete blood counts, etc., borderline, whatever. On February 28, 2005, the girl was admitted to a local medical center for combined oral and IV chelation therapy. And so the patient's blood electrolytes at admission were within normal levels. Initial medication orders included intravenous sodium EDTA and oral succimer, an agent primarily used for the treatment of lead poisoning. The medication order subsequently was corrected by the pediatric resident to intravenous calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA, 300 milligrams and 100 milliliters. At 4:35, she was administered 200 milligrams of oral succimer. Her vital signs remained normal throughout the night. At 4 o'clock a.m. the next day, a dose of intravenous sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams per deciliter, normal value for pediatric patients 8.5 to 10.5. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore a normal cardiac rhythm, and a cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 5 milligrams per deciliter. Despite repeated doses of calcium chloride, all attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. Can you believe that? It's an accident. You know what the accident was? Instead of injecting calcium EDTA, they accidentally injected sodium EDTA. But if you think sodium EDTA versus calcium EDTA, what's the big deal? It's the same thing, isn't it? Because a lot of people think, it's the same, it's close enough, but it's EDTA is EDTA. But no. You know, and this one, this goes on. Pennsylvania, 2005, 5-year-old boy with autism. Same mistake, sodium EDTA instead of calcium EDTA.
So one is better.
No.
One should be used instead of doing
Sodium is too strong. Sodium is not, sodium is very aggressive. They have it there, but that's the aggressive one. Calcium is the less aggressive one. And so they needed the more aggressive one to treat more severe, like adults with severe lead poisoning. But, and to bring the levels way down, something like that. And so you know what the CDC recommendation is? And this is old, so they probably did it. Get rid of the sodium EDTA. Don't need any more sodium EDTA because this deaths could have been prevented. But yeah, it's pretty sad. I mean, just, Anyway. So that's, what was I looking at here? And so those are some uses. This is sodium EDTA right here. Structure. EDTA. These are some products containing EDTA. Porphyrins are another example. I talked about these flat pancake structures. These occur in a lot of biological molecules. These are the porphyrin structures. And they have a whole bunch of different things you can attach to these. Chlorophyll's one, magnesium, and others which aren't in here. But there are a lot of biologically significant complexes. So what we're going to do is we'll look at this problem. And this problem, basically, what it is explain the following observations through a series of equations. The green solid, chromium. Now, chromium 3 chloride hexahydrate dissolves in water to form a green solution. And so when we look at this solution, what is it? How do you figure it out? And so for this particular problem, what I wanted you to do was I wanted you to go back in the book and see if you could find that complex. What do you think the complex is? Well, hexa-aqua probably, or tetra. Tetra-dichloro. Okay, where did you see that? Did you see it somewhere in the book? In the solutions manual? You could, yeah, I guess you could see it in the solutions manual. You know, this is one of the things that I was thinking. Actually, example 24-6, even though, and I realize that I probably assigned this at the wrong point, that particular problem, number 42. Because here we can see, it's going to be hexa-aqua chromium-3 chloride. Okay, this should be the green. Or is it? List the color of this is violet, whereas this color is yellow. Okay, then we look at some others here. And then based on these complexes, you know, cobalt 2 is pink, whereas this is blue. And so based on these, we can kind of get an idea. And so in this particular one, what we're doing is we're just using what's observed, you know, these facts to try to correlate it with what the identity of the species is. But that particular problem involves some digging around in the chapter to answer. It's not so easy. You know, you can't just sit there and figure it out. And so that one, don't worry too much about. You know, you aren't going to get a problem similar to that on the test. I wouldn't give that to you unless I gave you a whole bunch of other data in addition to that. Okay. What else? There was another question? No? All right. I'm kind of spending too much time here talking about this stuff. So let's look at the nomenclature for these. And so we see just in the book, the rules are here. Anions and ligands are named by using the ending O. Neutral molecules are just carry the unmodified name, except for 4 of them. And so, for example, ethylene diamine would just be used as ethylene diamine, the name of the molecule. But water would be called aqua. Ammonia is called amine with 2 M's. Carbon monoxide is not called carbon monoxide. Carbon monoxide is called carbonyl. And nitrogen monoxide is called nitrosyl. And so everything else we just name by its name. So for example, if carbon dioxide were to attach, we just call it carbon dioxide. Here. Those are for neutral molecules. And so aqua, water, amine, ammonia, carbonyl, carbon monoxide, nitrosyl, nitrogen monoxide. Okay, the number of ligands is given by a prefix. You know, the prefixes are mono, di, tri, tetra, penta, hexa. You know, typically we aren't going to have more than 6 ligands. And so we'll stop at hexa. Now there's a problem. Some ligands also have di in the name. If you look at this, do you remember ethylene diamine? I wrote that on the board right at the end as a bidentate ligand. Ethylene diamine, because it has 2 amines attached, this is just one molecule. And so the di here can be confusing. And so if we have what we call a ligand that contains one of these prefixes, we use an alternate prefix system. So if I wanted to say I have 2 ethylene diamines, would I say it like this? Diethylene diamine. If I said diethylene diamine, you'd think I had 2 ethylenes and 2 amines, which I don't. I want to have 2 ethylene diamines. And so we aren't going to use di, we're going to use these, bis, tris, and tetrakis. And so if I have 2 ethylene diamines, I'd say bis ethylene diamine. Bis ethylene diamine would imply that I have 2 ethylene diamine molecules attached to it. And so it would look like this. And so let's take a look. The structure of ethylene diamine is kind of interesting. You know, with these Lewis structures, these are all sp3, so I'm just going to arrange it like this so you can see how the 2 nitrogens can bond to one metal here. Putting a lone pair there. Here. And so this molecule is the ethylene diamine. And this is an example of a bidentate. Now, amine here is spelled with one M or two M's? One M. Like that. This is an example of a bidentate. It bites into the central metal with two atoms. And so if I throw in a cobalt here, and let's throw in a cobalt 3, then one of the nitrogens can bite here. Now the other nitrogen is going to bite in an adjacent position here. So we'll make it out like this. And so the coordination number of cobalt 3 can be 6. So we have 4 empty sites here. And so this will be NH2, CH2, CH2, NH2. Uh-huh.
The camera.
Oh, yeah, the camera. Thank you. Okay, now we have one ethylene diamine. So this is coordinated with one ethylene diamine molecule, but if you look at the coordination number is 2 from the 2 nitrogens. And so coordinated to one molecule in 2 places, therefore CN is 2. Now how many more ethylene diamines can we fit? 2 more. And the thing about ethylene diamines, they aren't long enough to stretch to opposite. So if I bind one here, I can't stretch it out to the opposite site. I have to stretch it to a 90 site or an adjacent site. And so the next one I can bind is here. But you know, it gets tiring writing this, doesn't it? And so we have a shorthand way of doing it. Like that. You know, the 2 nitrogens bind like this. This is a shorthand way. And the same thing here. Yeah. And so now I see I have 3 ethylene diamines bonded. And so it's coordinated to 3 molecules, but its coordination number is 6. Do you see the difference between coordination and coordination number? You know, this is only 3 molecules, but a lot of people say the coordination number is 3 because there are 3 ethylene diamines. You know, how would we name this? Well, to write it, the formula, we always write what first, the metal or the ligand first? The metal. And so the metal, which is cobalt 3, and then we write the ligand. Now the ligand, we have an option here. The option is we could use the shorthand way, which is En 3 plus. Each ethylene diamine is neutral. And so this would be called triethylene diamine, cobalt 3 ion, or yeah, this is called tris. And sometimes we'll put parentheses around this to emphasize that it's 3 ethylene diamines. So tris ethylene diamine, and then there should be no space here. It's all one word. Cobalt 3 ion. Tris ethylene diamine, cobalt 3 ion.
There's only one M because
It's not NH3. The only time we have 2 M's is when it's NH3. This gives you a second clue because a lot of people will think, oh, diamine, I have 2 NH3s. But one clue is there's only 1 M. And so it's probably not 2 amines. It's probably something like this, ethylene diamine. So here bis, do you see this bis? Ethylene diamine means 2 ethylene diamines. We could spell it out like this, or we could write the abbreviation En in the formula. The other alternative is, this just makes it more complicated. If we do tris and then write out the formula, NH2, the condensed structural formula, CH2, CH2, NH2, 3. Basically the same thing. All right, let's continue on here. When we name a complex, ligands are named first. And so when we write the formula, the metal comes first, but when we name it, the ligands come first. So it's flipped. In alphabetical order, followed by the name of the metal center. The oxidation state of the metal center is denoted by Roman numeral. If the complex is an anion, the ending 8 is attached to the name of the metal. So we'll take a look at some more of these here. Look at this one. How would we name this? It's CrCl2H2O4. Tetra, aqua, dichloro, chromium, Roman numeral 3. And so that's what we have here. Tetra, note the double vowel. Tetra, aqua, dichloro, chromium, no space, Roman numeral 3. How would we name this one? Well, dichloro would come first because C comes before E. And so this would be dichloro, bis, ethylene diamine, cobalt 3 ion. How would you name this one? Tetrahydroxo. Now we'd like to call it tetrahydroxo chromium 3. But when the complex has a net negative charge, we change the ending of the metal. And so rather than tetrahydroxo chromium 3 ion, we call it tetrahydroxo chromate ion. The 8 on the end here tells me the whole thing carries a net negative charge. Let's look at this one. CuCl4 2 minus is called tetrachlorocuprate. And the Roman numeral charge on copper is +2, so it's cuprate 2 ion. This is an interesting one here. How about this one? This is carbon monoxide, but if it's carbon monoxide, we don't call it carbon monoxide, we call it carbonyl with a YL. And so this is called hexacarbonyl tungsten 0. And so we put parentheses 0. So look at hexacarbonyl tungsten 0. Now some metals have a funny name when you add the 8. So for example, let's say the complex, the whole thing carried a net negative charge and you had iron. You wouldn't want to call it ironate. Ironate sounds too funny, so we call it ferrate. Copperate sounds funny, so we call it cuprate. Tinate, stannate, silverate, argentate, leadate, plumbate, goldate, orate. And so for these, we change the name of the metal. And so if you see iron in a neutral complex, we just call it iron. If you see an iron in an anion complex, we call it ferrate, etc. All the other metals we just use as is. So cobalt would be called cobaltate. Cobaltate is fine. Here. When we write the formula, the chemical symbol comes first of the metal. So the metal comes first, followed by the anions, and then the neutrals. And so the metal followed by the anions. Now look what we do with the anions. We do the anions in alphabetical order. And so chloro comes before nitro. Actually, nitrito. Nitrito. Because we have nitrato and we have nitrito. And so how would we name this? We would name this one, well, chloronitritoamine. Which one will go first? Amine. Tetraamine, chloro, nitrito, cobalt, 3. It's going to be +3, -1 gives me +1. In names and formulas of coordination compounds, cations come first, followed by anions. And so look at this, we have a complex cation and a complex anion. So let's name this one. This would be tetraamine platinum 2. So the whole cation name's tetraamine platinum 2, all one word. Space, and then the anion name. tetrachloro platinum, but it's negative. And so it's got to be called platinate 2. Because this is -4 plus 2 gives me -2. So this is -2 anion. Yeah. All right, how late do I go till? 55. I'm out of time. Wow. I didn't make it very far. Behind schedule. So yes. We aren't going to have a test this week. We'll have a reactions quiz this week, Thursday. Test will be next week on chapter 24. What's that? Tuesday, probably. Let's see.